Okay. Um, so I want to wrap up the class by sort of closing the book on some more stuff we can do with the machinery of unbiased prediction that we've developed over the last few lectures. So just sort of remembering what we've done with it so far. First of all, we've seen how to use this machinery to make calibrated predictions. This was sort of by definition. These were predictions that were unbiased, conditional on the predictions themselves. And calibrated predictions had all sorts of good properties. It was sort of a dominant strategy amongst all policies, mapping predictions to action, to just trust the predictions and act as if they were correct. Okay, so you can think of this as sort of maybe the foundations for the semantics of trustworthy machine learning. What is the promise you're supposed to trust in trustworthy machine learning? Well, calibration has sort of a good candidate there, which is that you should act as if the predictions are correct. Trusting the predictions is a good idea. But on its own, calibration in high dimensions had a number of problems, mainly that sort of both the statistical and computational complexity seem to be exponential in the dimension. Okay. So then last time I delivered a lecture, we saw that if all you wanted was one of the corollaries of calibrated prediction, namely that for a fixed collection of downstream decision makers who best respond to the predictions, they should all have no swap regret, then calibration was overkill. Actually, it was sufficient to ask for predictions that were unbiased, subject to the best response correspondence of each of the downstream decision makers. That is, for each particular downstream decision maker, if they're going to best respond to our forecasts, that's going to bucket the predictions we make, even though there's exponentially many of them, into just k buckets, one for each action they might take, right? Mapping the predictions to the action that is the best response. So there's only like k such events for each downstream decision maker, and if we're unbiased subject to these, that's enough to guarantee all of them diminishing swap regret. Okay, so like you can think of this as some kind of coordination mechanism for maybe agents who are not sophisticated enough to run their own no swap regret algorithms, maybe, but are sophisticated enough to best respond to forecasts. Okay, but just as like an algorithm, like if there was only one decision maker, okay, and we were just using this as an algorithm to make predictions that are unbiased, subject to like the best response correspondence of this one decision maker and then best respond to them, this wouldn't have had very many advantages over the sort of existing algorithms that we gave already for swap regret and subsequence regret, right? Sort of it's a roundabout way of getting there. We had to sort of, solve various zero-sum games, like essentially numerically by simulating play of a zero-sum game. It wouldn't have given like a new algorithmic result. And so, okay, what I want to do today are give sort of two applications of this technology to solve problems that we didn't know how to solve before. Okay, to give sort of no subsequence regret in games with very large action spaces, online combinatorial optimization games. So think about things like online shortest paths, where every day what you're doing is you're picking a path in a network. Okay, and if we have time, maybe I'll just wave my hands at the problem of producing prediction sets in k-label prediction problems. So think about, like an ImageNet kind of classification problem where every day you see an image and you have to assign a label to it, like stop sign or hot dog or chinchilla or whatever. Okay, maybe there's like 1,000 labels. And what you want is to be able to express your uncertainty in your predictions. And so ideally, you would say, like, for sure, this is a hot dog. I'm 100% sure that this is a hot dog. But if you've got some uncertainty about that, you might want to say, I've got a 40% belief that this is a hot dog and a 60% belief, and a 50% belief that this is a stop sign. And so in particular, like here's a set of two labels, hot dog and stop sign, that I think have a 90% chance of being correct. Okay, so producing a prediction set is, the goal is to produce a small collection of labels, okay, ideally just one label, but a small collection of labels that have the property that they contain the true label 90% of the time. Okay, so just like sort of online combinatorial optimization kinds of problems, there's a combinatorial explosion problem here. If I've got k labels, there's 2 to the k prediction sets. Okay, and so the question is, what can you do in this setting that sort of has computation time, and statistical bounds scaling only with k, not with 2 to the k? Okay, so both of these are sort of problems where we want guarantees against adversaries in hindsight, in settings where the action space of the learner is very large, it's exponentially large. Okay, and so we can't use the kinds of technologies we've developed in this class that scale sort of in proportion to the number of actions. Okay, so the kinds of things we used for getting subsequence regret, for example, and we need to do something else. And this machinery we developed of producing unbiased predictions, that's going to be the something else. Yeah. Yeah, good. We know some stuff about the batch version of the problem, but the thing I'm going to describe today would be useful even in the batch setting. Like basically prior work for sort of the batch version of the problem has the flavor of, trying to project the problem onto like a one-dimensional problem to avoid this curse of dimensionality, and then doing clever things to solve the one-dimensional problem. But obviously a lot of information is lost projecting it onto the one-dimensional problem. What we're going to talk about today is a way to solve this problem without needing to do this one-dimensional projection. Okay. Okay, so online combinatorial optimization. Let me remind you of what this is. We sort of mentioned it briefly when we talked about follow the perturbed leader and online linear optimization. But basically, it's like an online instance of the expert setting, but where the experts consist of subsets of some D base actions, maybe subject to a combinatorial constraint. So again, you should have in mind things like online shortest paths, where there's some underlying graph, and your action set is perhaps ST paths in this graph. There might be a lot of them, but they are, I don't have to, there's D base actions, like the edges in the graph, that they are sort of composed of. Okay, and the important thing is that the gain that the learner is going to have in a scenario like this isn't going to be arbitrary. It's going to be the sum of gains that are decomposable along the base axis. Okay. So an online combinatorial optimization problem, it's defined by a set of D base actions. Let's call these B. Okay, so think about these maybe as like the edges in a network. A set of actions A that is some subset of the set of all subsets of the base actions. Okay, so the action, each action is a subset of the base actions. Like a path in the network is a subset of edges. Okay. And in rounds, the learner chooses a distribution over actions. Okay, so like a distribution over paths in the network, say. The adversary chooses a vector of gains. Each gain is a number between 0 and 1, and there's one of these for each of the base actions. Okay, so think about choosing like a congestion on each of the roads in the network. The adversary is not choosing a separate number for each of the sort of compound actions, of which there might be exponentially many. They're choosing gains at the granularity of the base actions. And then the learner gets some utility. That I'll write like this. The utility that the learner gets when they pick a distribution PT over actions and the adversary picks a vector of gains is the expectation over an action drawn from the distribution of, well, what I'm going to define in a moment, the utility that the learner gets from a particular base action given the vector of gains. And what is this? It's just the sum over all of the base actions in the compound action chosen by the learner of the gain of that base action. Okay, so the action space for the learner can be complicated. Okay, it could be it's not all subsets of the base actions, it's some structured subset, so all paths in a network, all spanning trees, any combinatorial structure you like. There's no restrictions there. Okay, so the action set is large and in some sense arbitrary. The actions consist of subsets of the base actions, but any subset would define an online combinatorial optimization game. As usual, the learner is allowed to randomize sort of what gives this game structure. It's sort of the structure that we saw in online linear optimization. The problem that we solved when we wanted external regret with follow the perturbed leader is that the utility that the learner gets is linearly decomposable across the base actions. So it's the sum of the gains obtainable by each of the base actions. Okay, makes sense. Okay. So we saw how to get no external regret in settings like this by reduction to sort of a best response oracle, an online optimization oracle. So what follow the perturbed leader did is it sort of said, okay, suppose I have the ability fixing the gains G to compute a best response, to find the feasible action A that maximizes the sum of the utilities. So in online shortest paths, that's Dijkstra's algorithm, computing the shortest path in a graph. Then, follow the perturbed leader was a reduction to this oracle, this optimization algorithm that would guarantee, in time polynomial in the number of base actions, a regret bound, an external regret bound scaling with something like the number of base actions over root T. Okay. Now, suppose we wanted a more sophisticated form of regret. So suppose we wanted a subsequence regret or swap regret. Okay. Well, and sort of, we know how to do this via the algorithms we developed for subsequence regret and swap regret, just to sort of remind ourselves of what these things might mean. Subsequence regret is going to ask for regret, not just overall, okay, but simultaneously on various subsequences that can be defined by external context as well as our own action. Okay, so we could ask for, in an online shortest paths example, no regret on all of the days for which the route that we pick includes I-76, or no regret on days, for which it is raining and we pick routes by the river or anything like that. Okay. The algorithms we saw for this, that we sort of derived as an example of our sort of multi-objective optimization framework, ultimately, they required like writing down a matrix whose width and length, that's matrix oriented, scaled with the number of actions. Okay, and solving some operation therein. Okay, and here the number of actions is truly enormous, right? It's like 2 to the d potentially. So any algorithm that directly involves operating in action space without taking advantage of this sort of linear structure, it's going to have running time scaling exponentially with d. Yeah. Let's see. If the action space contained the singleton actions, then you're saying you could run multiplicative weights. Well, that would give you no regret over the singleton actions. Well, it depends what the feasible, there are extreme, depends what the feasible region is. If your action set was the simplex, or the extreme points of the simplex, right? So multiplicative weight solves this problem. Like the standard experts problem is just the case where, your action space is just the simplex over B. Multiplicative weight solves that problem. But in general, the singleton actions are not the extreme points for like the shortest paths problem. So even if I said your actions are paths in the graph plus any single road segments, that wouldn't solve your problem. Not weighted average. It's the sum over them. And the maximum, if you were going to try to maximize over all of your actions, would be over the action space. So like all paths in the graph, say, right? It's a maximum over some combinatorial set that has structure. That's right. It's not averaged, it's summed. You can't. All of the roads are not a path. Yeah, if you can play all the actions and the gains are non-negative, then like you should always play all of them. Yeah. So like, the difficulty of this depends a whole lot on what the action set is, right? If the action set is just singletons, then it's just an expert's problem with the expert's multiplicative weight solves. If the action set is all subsets and the gains are non-negative as I've defined them, it's a trivial problem. You just play everything every day. The reason it's not in general a trivial problem is because there's some structure on what the action set is. Yeah. Yeah, good. So let's talk about rates for swap regret, right? So if we used these sort of fixed point algorithms, the kinds of things we derive from multi-objective optimization, we would sort of pay, even in our regret, a polynomial term in the number of actions, like root number of actions, which here is exponential in D. So there we'd get like root number of actions over root T regret. Now this algorithm that Natalie presented in class, which is brand new, you could run that. You could use that with sort of follow the perturbed leader as a subroutine and get no swap regret at some rate that would sort of be like polynomial in D over log T. So it would be, we'd sort of get a good dependence on the number of actions, but a terrible dependence on T, right? So you'd have to run for sort of exponentially many rounds to get very small regret. The one thing that's going to come out of the application we see today is that in online combinatorial optimization games, you can get swap regret scaling sort of with polynomial in D over root T. Okay, so simultaneously get the log number of actions and the correct 1 over root T dependence. Okay, so the algorithm Natalie showed us it wasn't sort of an improvement. It wasn't a strict improvement over these sort of general fixed point algorithms. You got an exponential improvement in the number of actions, which is good in large action space games like this, but you paid for it by an exponentially worse bound in time. One corollary here, information theoretically, it's not going to be efficient in this case, but one corollary here is swap regret in these games that it will scale, will scale with the log of the number of actions. So polynomial in D, and also get the correct 1 over root T bound. Okay, and the reason we can do that is because there's structure here. So it's going to be efficient for subsequence regret. It'll run in time polynomial in the number of subsequences. But for swap regret, which is subsequence regret where for an exponential number of subsequences, one subsequence for every action, this will not be a computationally efficient algorithm, although the information theoretic bound will be good. That's right. So compared to sort of these new algorithms that Natalie showed us, this will get a swap regret bound that is exponentially better in terms of T and gets the same dependence on D, but computationally it will not be efficient. Yeah. Yeah. Yes, yeah. So that's a special case of subsequence regret, right? So I could say I want subsequence regret where the subsequences are all of the days for which I played any particular road, and then the guarantee I will have is all of the days for which I took Pemberton Street, I do as well as the best fixed path in hindsight. Yes, so if you condition, like you can get no regret conditional on any polynomial number of events, which you can define however you like. For example, days when you play particular base action. That's right. So we'll like all of this will be just corollaries of best responding to forecasts of the games that are unbiased, subject to a number of events that we will see is going to scale only with D, the number of base actions, cross the number of subsequence indicators that you care about, right? So if you want no swap regret, or not, if you want no regret conditional on playing any of the base actions, that's just D subsequences. Okay, good. Okay, let's just remember what subsequence regret is. So, given a subsequence indicator function, remember this is a function which maps history cross action cross context to a number between 0 and 1, which you can think of as indicating whether today is part of the subsequence or not. The regret that I have on some transcript pi to a particular subsequence E and a particular action A. This is one of my compounded actions, so there's a lot of these actions, is just the sum over all of the time steps of the expectation of my distribution at each time step of the indicator for whether subsequence E is active times the difference between my utility if I were to have played action A minus my utility given what I actually played. Okay, so it's just my regret to action A, except I'm selecting, it's not summed over all of the rounds. I'm selecting out the rounds corresponding to this particular subsequence. And the goal, given some collection of subsequence indicators E, I'd like that the maximum over all of the subsequences in this set, and also the maximum over all of the actions I've got of my regret to the worst case subsequence and the worst case action, that should be bounded. Okay, now we're gonna give algorithms that have running time that will scale sort of linearly with the number of subsequences. Okay, so for efficient algorithms, think of the number of subsequences as a set growing polynomially with D. But we are still asking on each of these subsequences for no regret to the best action, and there's exponentially many actions. So this is a maximum over sort of exponentially many objects here. Okay, so again, swap regret would correspond to a subsequence which was equal to the indicator function that you played each possible action. There's exponentially many of those. But, you know, like I could define something like, you know, subsequences defined by particular base actions that I play something that includes a base action, or I could categorize my actions like scenic routes and routes that use toll roads or whatever, and I could ask for no regret on those subsequences. So we have a swap regret kind of flavor. Okay. All right. Okay, so the claim is going to be that to achieve no subsequence regret, all I need to do is to best respond to forecasts for the gains that happen to be unbiased, subject to some modest collection of events. If we can do that, we have an algorithm because we know how to make forecasts that are unbiased, subject to modest collections of events. And so the question is, what are the events? Okay, so first, let me just remind you of the best response function. Given a vector of gains, G, the learner's best response to those gains is just, well, the action that would maximize their utility given those gains. Okay, so it's the action that maximizes among all of their exponentially many actions their utility, which remember, because this is an online combinatorial optimization problem, what's their utility if they play an action? Well, it's the sum over all of the base actions contained within the action they play of the gain of that base action. Okay, so this is the best response function. So first of all, the algorithm I'm going to be talking about is always going to be produce a vector of forecasts for the gains, G hat, and then play this action. Let's just break ties in some consistent way. If there's multiple best response actions, always pick the lexicographically first one, say. Okay, so the first kind of event I want to talk about is the following. For each of the base actions, let's define the event EB, B for the base action, given the vector of gains, which is just the indicator that the base action is contained in the best response action given the gains. Okay, so I forecast some gains, like a congestion on each of the roads in the road network. You best respond to those gains, you find a shortest path in the road network. There's an event for each of the roads in the road network, which is just, like on the path that you played, having run Dijkstra's algorithm, having best responded to the forecasts, did you include Pine Street? Did you include 23rd Street? Did you include Pemberton Street? Okay, so these are the events. And just sort of maybe for some intuition, remember, how did we get swap regret? Right? What were the events we needed to get swap regret for downstream agents who were best responding to our forecasts? Well, the events were, did the forecast we make cause you, when best responding, to play some particular action? That was enough, we showed, to get swap regret for downstream agents. Now, there's too many such events in our case if we want to run in polynomial time, because there's potentially 2 to the d actions. Okay, so we can't use those events. But these events are sort of similar. It's saying, when you best, did the forecasts we make cause your best response to include one of the base actions? Okay, there's only d such events. Okay, so these are going to be important events for us. Okay, now, clearly these are not enough to give subsequence regret guarantees for a particular collection of subsequence indicators, because we haven't yet made any reference to the subsequences, right? We're gonna, if we have subsequences we care about, we're gonna have to use them in some way. So we'll define some more events. Given a collection E tilde of subsequences, let's define the following collection of events. Okay, a collection of events which is going to be parameterized by E tilde and by the set of base actions. This collection of events will have one event for each pair of a subsequence indicator function in E tilde and a base action B. And given a history, given a forecast, and given context, this event is going to be the product of the subsequence indicator function that sort of says, okay, given the history, given that the action played is a best response to the forecasts, and given the context, is today a member of the subsequence E tilde that we care about, times this event EB. And did the action played today when best responding to the forecast include base action B? Yes or no? Okay, and we've got one of these compound events for every one of the subsequences we care about, and for every one of the base actions. Okay, so first of all, the number of such events we're talking about here is the product of the number of subsequences we care about times d, the number of base actions. Okay, and what is each of these events? Well, each of these events asks the following yes or no question. Given the forecasts, the learner who best responds is going to play some action. Okay, the question is, when they do that, which can determine in particular whether today is a part of the subsequence we care about or not, it's asking yes or no, is today a part of subsequence E tilde? And did you play base action B today? Okay, so these events are defined by all pairs E tilde and B. That's right. It's like the it's the product of the original event space and the indicator for whether you played each of these base actions. Yeah, it's not clear you can but yeah, that's right. You're taking the sort of original subsequence indicators and you're sort of further refining them by taking the intersection of the indicators for whether you play each of the base actions. Okay, collection of events makes sense. Okay, so this is a collection of events. Oh, yeah. Yes, exactly. Yes. Um, I don't know. Each of these is a function that takes g as input. No, so this is a collection of functions. These functions take g as input, right? So we're going to ask that our forecasts of g, we're going to make forecasts like g hat of g. We are going to ask that they are unbiased, subject to this collection of events. So the events are active or not as a function of what g is. And this is a collection of mappings from, among other things, g to indicators. Does that make sense? Okay. Okay. Um, okay. So what's the theorem going to be? So fix a d-dimensional online combinatorial optimization problem. And a collection of subsequences, subsequence indicator functions. E tilde. Um, let's let the state space for a online prediction problem be the set of all feasible gains. Okay, gains are, numbers between 0 and 1, one for each of the base actions. That's the kind of object we're going to be predicting. Um, fix the transcript predictions pi t. We'll call our predictions of the gains g hat, so g hat 1 through g hat t to disambiguate the predictions from the real gains. And let's suppose these predictions have bias at most alpha, conditional on the events that we just defined. Okay, so the events defined by our subsequences and base actions. And let's also, for good measure, ask that they be unbiased, conditional also on just the subsequence indicators, not intersected with the base action. Okay, so if we've got E subsequences we care about, this is E times D plus E different events. Okay. And now suppose the learner best responds to our forecasts. So suppose the action played at day T is just the best response to the forecasted gains. Okay, so this could either be a behavioral assumption about some downstream learner who's doing this, or this could be our algorithm. We could say our algorithm is we're going to make these forecasts and then choose an action by best responding to them. Okay. then the claim is that the subsequence regret, okay, so the maximum over all of the subsequences we fed into our algorithm, and also the maximum over all of the exponentially many actions we've got of the regret that we have on this subsequence to this action is at most 2 times alpha times d. Okay, so bias of alpha of our gains sort of is going to translate into regret of alpha times d, alpha times the number of base actions for our actions. Okay, does the statement make sense? Okay, and just remember that like we know how to do this without, we know how to do this efficiently in the number of subsequences with alpha going to 0 at a rate of like log of the number of subsequences over root t. Okay, so we're going to get the right root t bounds that we're hoping for. We get sort of nice computationally efficient algorithms for any polynomial number of subsequences. And even if we were to ask for swap regret, even if we were to include a subsequence corresponding to the indicator function for each of the 2 to the d possible actions, because our bias goes to 0 only with the, depends only on the log of the number of conditioning events, we would still get a polynomial dependence on d over root t here. Although then we wouldn't know how to make these predictions without running time scaling with the number of actions. Okay? The statement makes sense? Yeah. I haven't proved this theorem, if that's the question. Or what do you mean? Oh, you're saying like, is there some intuition for why this approach is able to get efficiently these subsequence regret bounds? Okay, so the, like I've already told you how to make predictions that are unbiased subject to arbitrary collections of events efficiently. And I'm going to prove this theorem, but like, here's the statement of the theorem. So the algorithm is just going to be a combination of these two things, right? Like, if you want subsequence regret bounds, it suffices to be unbiased subject to this small collection of events. And we already know how to do that. So there's no, like, this is the only thing to prove. That there's no new algorithmic thing to tell you, because the algorithm underlying this is just our algorithm for making unbiased predictions subject to collections of events. But if you're looking for sort of intuition for why through this approach we're able to efficiently get subsequence regret bounds and get sort of information theoretically like exponentially better swap regret bounds compared to sort of generic approaches that have dependencies on the number of actions, it's because the generic approaches are not using the sort of special structure of this problem, which is that everything is sort of, which is that there's a d-dimensional reward space that sort of underlies the 2 to the d-dimensional action space. And so things like these fixed point algorithms, they're working directly in action space. Because our underlying algorithm is making predictions in reward space, we are able to operate in reward space in which, like reward space is low dimensional here, action space is high dimensional. And sort of Blum-Mansour kinds of algorithms have no, because they're explicitly operating in action space, they have no way to exploit that structure. Sort of the algorithms that Natalie talked about last time can sort of exploit that structure because they get to run subroutines like follow the perturbed leader that exploit that structure, but they inherently have this terrible dependence on the time horizon. And so here you can exploit that structure while still getting the right one over root t bounds. This, what these events are. Yeah, cool. So maybe you're getting at sort of a confusing piece of notation that I sort of slowly backed myself into over the course of the semester, which is that we've talked about two very similar objects with very similar notation, and they're both showing up here again. One is events that we are unbiased with respect to when we are predicting, in this case, gains, okay? These are essentially subsequences, but they are functions of our vector-valued predictions. The other is subsequences in the learner's action space. Okay, these are like the subsequence of days for which I play action 5. These are functions of an action, not of a prediction. Okay, so here we're using both of them confusingly, which is why I've put tildes on some of them. Okay, so these events EB, these are functions of predictions. Okay, it is activated by a prediction G if when best responding to this prediction, base action B is played. These subsequences E tilde, these are functions of actions. Okay, this is like the subsequence of days for which it rained and you played action 12. Okay, now of course, when I make a prediction, that maps onto an action through the best response function. And so these events, which are functions of predictions, because I'm going to ask that my predictions be unbiased subject to these events, what do? Well, they say, okay, when I map this prediction onto an action by best responding to it, first of all, is subsequence E tilde activated? Yes or no? If yes, did the best response to G play base action B? If both of those, if the answers to both of those questions were yes, this evaluates to 1, otherwise it evaluates to 0. It means, so what is subsequence regret? I mean, it means that E maps to 1, okay? This is a function of the actions. Okay, so this is, when we're talking about regret, we're operating in action space. We're saying on the subsequence of actions for which this event was active, would you have done better off on average playing some fixed action A given what you really did? If all you wanted was, yeah, no regret on the subsequence of days for which you played each of the base actions, then this collection of events would be the same as this collection of events. So it would just be this collection of events. But more generally, you can care about other events. Yeah. Mm-hmm. You get better regret bounds, right? So like, again, think about instantiating, when I remind you of what alpha is, this will become more obvious. But let's say you run, Blum-Mansour to get full swap regret, okay? Your regret bound is going to be like root the number of actions over root T, okay? The number of actions here is like 2 to the D. Okay, now what alpha are we going to get if we instantiate this with full swap regret? Okay, the number of events is going to be like 2 to the D, But the bias that we get, alpha, depends on log of the number of actions over, log of the number of events over root t. So that's like log of 2 to the d. That's like d over root t. So we will get a bound that scales like polynomial in d over root t. So it's not, right, so it's not just a computational advantage when the number of subsequences is polynomial. It's also getting a better bound because our dependence is polynomial in the dimension, which is like log of the number of actions. And sort of, because we're approaching this from a very different angle, we're sort of operating until the very end when we best respond, we're operating in reward space. So if we inherently get to take advantage of the fact that this is a, low dimensional problem in reward space, it's only high dimensional in action space. Does that make sense? So I guess it's yeah, maybe in the regime where this is efficient, namely that there's a polynomial number of subsequences, there's no meaningful distinction. Anyways, but let me highlight mainly the computational aspect. Yeah. Okay. All right. So let's prove this, and it's going to be a very direct calculation given how we've set things up. Okay, so let's fix. Yeah, we need to prove something about the maximum of this quantity over all subsequences and actions. Let's fix a particular subsequence and a particular action to care about. Okay, so we can directly compute what is our utility on this subsequence given the actions we play. Okay, so it's just the sum over all of the time steps of the indicator for whether subsequence e tilde is active at time step t times the utility that we get given the action we play and given the gains chosen by the adversary. And we can expand this out. We know what our utility function looks like because it's an online combinatorial optimization problem. This is just the sum over all of the rounds of the indicator for the subsequence times the sum over all of the base actions in the compound action that we played of the gains of that base action. Okay, so just writing out the definitions here. Okay. Now I want to do two things. Okay, I want to, first of all, interchange these two summations. I want to sum over the base actions first, then over the time steps. That's fine. And then I want to rewrite a sum over the base actions that are contained within the action we play as the sum over all of the base actions of the indicator that the action is contained in the base action is contained in the action we've played times the gain. Okay, both of these are just syntactic changes. Okay, so this is equal to the sum over all of the base actions of the sum over time of the indicator for the subsequence we care about times the event, given our prediction for the gains, that the base action is contained in the best response to our prediction, which, remember, is equal to the action we play. Okay. Times the gain of that base action. Okay, so like what's gone on here, up here I was summing up over only those base actions contained in the action we play. First I observed that's the same thing as summing up over all of the base actions of the gain times the indicator that the base action is contained in the action we play, because anything that previously wasn't in this sum is zeroed out by the indicator. Once I've done that, this sum is over all of the base actions. It doesn't depend on time, and so I can interchange the summations, which I've done. Okay? But now, what do I have here? Well, it's the sum over all time of the real gains, not the predicted gains, but multiplied by one of these events that I've defined over here. This is an event that we are guaranteed our forecasts are unbiased on, up to bias alpha. What does that mean? Well, it means that even though our forecasts day by day might be very different from the actual gains, that as summed up over all of the days and weighted by events that look like this, our forecast gains look like the real gains. Okay, which means that we can replace here the real gains with the forecast gains, so long as we are willing to pay for an alpha bias term. Okay, so this is larger than the sum over all of the base actions of the sum over all time of the indicator of whether the event we care about is active today times the event that base action B is played when best responding to the forecasts times not the real gains, but actually the forecast gains. Okay, and what I've paid for swapping out the real gains for the forecast gains is an alpha term in every, for every single one of the base actions. There's D base actions, so I've lost potentially an alpha D term here. Okay. Now, okay, what is this? Okay, we are summing up overall time and then summing up over all of the base actions that are part of the best response to G hat. Okay, so we're summing up over all of the base actions that are part of the best response to G hat. And what we're, the gains we're summing up are not the real gains, but the forecast gains G hat. So this is the utility that we would get if we best responded to gains G hat, and the gains really were G hat. Okay, so this is the sum over all time of the indicator that the subsequence we care about is active times the utility that we would get if we best responded to forecasts G hat. That's what we actually did. And then the part that is different from what actually transpired is that the forecasts actually were g hats rather than g. Okay. Now, if the forecasts really were g hats, it was a really good idea of us to best respond to g hat. In particular, we can't have done better playing any other action. Okay, in particular, we can't have done better playing action A. So this is only larger than the sum over all time of the indicator that the subsequence we care about was active today, times the utility we would have gotten by playing action A instead of this best response when the forecasts, when the gains really were g hats. Okay, and this is just because once we're in the world in which the gains are what we forecast, we are playing optimally day by day, right? Like we're playing pointwise optimally because we're best responding every day to the gains. So you certainly couldn't have done better by doing anything else, by playing this other action A. Okay. Now, this looks a lot like what we want in the end. What we want to argue in the end is that our reward, our cumulative reward on this subsequence E tilde, given what we actually played, is at least as good as what it would have been playing any other fixed action A, which is sort of what we have here. Except, like here we are computing our utility as if the gains actually were our predictions when they weren't, right? The gains were G, not G hat. Okay, and so what we need to do is repeat this argument one more time to transition from G hat back to G. Okay, but we can do that again because by essentially the same argument, our predictions are unbiased on the subsequences that are relevant. And so when we do that, I won't repeat the whole argument. When we do that, we lose another alpha D, moving back from G hat to G. So basically, the chain of operations in this argument is the same as it was for swap regret last time. It was, we look at the utilities we have for playing what we actually play. Okay. Then we use our low bias property to transition from the real gains to the forecast gains. In the world of the forecast gains, we knew we were playing optimally. And so now we can say, well, what we actually did is better than what we could have done. And then we have to use our bias property once more to transition from our forecast gains back to our realized gains. Every time we fixing the action, the bias property lets us transition from forecast gains to realized gains or vice versa. Once we're in the world of forecast gains, we can transition between actions because if we're playing the best response action, we know that's better than any other action, right? So we go from actual actions and actual forecast gains up to actual actions, we go from actual actions and real gains up to actual actions and forecast gains, over to counterfactual actions and forecast gains, down to counterfactual actions and real gains. Every time we traverse one of these up to down edges, it costs us an alpha term. Okay? And so, moving back to real gains, we get that this is at least the sum over time of the indicator that we are a member of the subsequence E tilde that we care about, times the utility that we would have given that we consistently played action A on this subsequence, evaluated now at the real gains, and in moving back to the real gains, we've paid another alpha D term. So we, in the end, it cost us 2 alpha D. Yeah. Mm-hmm. Um, let's see. I'm not sure I totally understand the question, but let me try to parse it. Okay, so first of all, yeah, like forget about all of this like coordination mechanism stuff we've been talking about. Let's just think about this as like an algorithm design paradigm. We are designing an algorithm to get diminishing subsequence regret in online combinatorial optimization games. How does the algorithm work? We're just going to use our machinery for making unbiased predictions, unbiased subject to these events, and then we have a mapping from predictions to actions that we're going to use to choose an action every round. What's that mapping? It's just the best response map. Okay, so this is like the best response mapping, by the way, like is the same thing we just called like an offline optimization oracle for follow the perturbed leader, right? Follow the perturbed leader, you can also think about it as making like forecasts for the gains and best responding to them. Right, so very exactly the same algorithm paradigm. We're making forecasts for the gains now in a more complicated way, and we're best responding to them. Okay, so now like there is a fixed mapping from like gains to actions, and so this function is well defined. Like the gains we predicted, do they cause us to choose base action B or not? So what is the two-step thing? Like um sorry, but what is how come how is that different from follow the perturbed leader, where you are um like forecasting the gains in that case just by adding noise to the historical gains and then best responding to them? Yeah, let's see. So I mean, in some sense, like we also saw follow the perturbed leader sort of recently when we were trying to make predictions that would cause downstream agents to have no external regret. So um, yeah, so somehow like stability in the same sense as in the same way that sort of yes, follow the leader with stability, the thing that follow the perturbed leader gives you, is enough for external regret. External regret is sort of an unconditional guarantee. Swap regret, if you like, is a conditional guarantee, or subsequence regret is a conditional guarantee. And sort of, I think, therefore, it makes intuitive sense that the predictions you need to best respond to should themselves satisfy conditional guarantees. That they should be unbiased, as it turns out, conditional in various ways on your best response function. So if you like follow the perturbed leader and this algorithm, they're both in the same framework. They're two-stage algorithms that are working in gain space. They're sort of, if you want, forecasting the gains and then best responding to them. And here we're asking more of the gains that we're forecasting. We're asking for conditional guarantees, which seem necessary for things like subsequence and swap regret, which are themselves conditional guarantees. Maybe there's a, yeah, so I don't know if I have a better answer to your question. Maybe it's useful to revisit Follow the Perturbed Leader with this perspective, and maybe you'll learn something new about it. Okay, yeah. Um, yeah, I mean, so certainly like, so that's right. The forecasts are coming from a very different place now. They're coming from, this hedging kind of algorithm that comes from multi-objective optimization, where we've got a constraint for each bias condition. It's still randomized though. So in that sense, it's similar to Follow the Perturbed Leader, and it must be like you need randomized forecasts to, or you need the learner needs to be randomized to get regret against an adversary. And both in Follow the Perturbed Leader and in this algorithm, the learner is playing deterministically as a function of the forecasts, and therefore the forecasts themselves need to be randomized. So that's a point of similarity. But yeah, like Follow the Perturbed Leader is doing something much simpler. It's just adding noise to the history. Whereas here we're sort of keeping track of, the bias conditional on each of these events, and we're, solving a min-max problem to guarantee that the bias doesn't get too large in any of these buckets. Okay. Yeah, I think these are very interesting questions. And if you sort of went back and either learned something new about Follow the Perturbed Leader or took insights from Follow the Perturbed Leader to give more practical algorithms for making these unbiased predictions, that would be great. Like in particular, let me just highlight Follow the Perturbed Leader is a reasonably practical algorithm. Like you just compute history and add noise to it. This algorithm we gave for making unbiased predictions, it is polynomial time, it is efficient in the technical sense that computer scientists speak of, but it is a much less reasonable algorithm to actually run than Follow the Perturbed Leader. It requires solving a large zero-sum game using Follow the Perturbed Leader at every step. Right, so it would be great if there was a way to do this with sort of a more direct algorithm. That's right. That would be cool. So it's like at various times in this class, we have taken algorithms that we originally derived as solving abstract min-max problems. And using structure of a particular problem, we've sort of specialized them to combinatorial algorithms of various sorts. We did this for action-independent subsequences. We did this for swap regret. We did this for making unbiased predictions in the one-dimensional calibration problem. And so in general, this algorithm for making unbiased predictions for sort of arbitrary collections of conditioning events, it's in this abstract form, solve this min-max problem, which we know we can do efficiently, but but it's annoying. It is possible that for particular problems, if you want to use it like this, like maybe, if it's just to throw a random combinatorial structure out there, if it is Follow the Perturbed Leader and the subsequences you care about are just the subsequences for which you played each road segment, it's possible that there you don't need to solve the abstract min-max problem. There's special structure, and the min-max equilibrium has some nice combinatorial form. We've seen instances of that happening throughout the class. I don't know of instances where it happens here, but mostly for lack of looking. I wouldn't be surprised if there are special cases for which you don't have to run the min-max computation in the abstract, and finding those would be very interesting. That's right. Yeah. So yeah, good. So like, yeah. So maybe just like trying to digest that a little bit. Calibration gave all sorts of nice properties. Okay, but you know, calibration was prediction in a way that was unbiased, conditional on the prediction itself. There were these. It was this very strong thing we were asking for: exponentially many conditioning guarantees. We noticed that for the purposes of swap regret, we didn't need all of those guarantees. We could sort of compress them down, compress the bias conditions down into this much smaller collection of buckets defined by the best response correspondence. But now what you're saying is like, even though we've done that and we're asking for predictions, we're asking for constraints on our predictions that are bucketed by the best response correspondence, we are still dealing in predictions. We're still making all of these varied predictions. It's just we're not measuring their bias except as measured by the best response correspondence. You are now suggesting, I think, that it might be that we can squash things down even further. We don't even need to deal in these predictions. Maybe there's some implicit way to sort of deal only in the best responses and nevertheless sufficiently recover guarantees like this. That could well be. That would be cool. Yeah. So that would be cool. Like in particular, right? This is an efficient but not reasonable to run algorithm. If you could have one that got the same kinds of guarantees but was actually reasonable to run, even in various special cases, that would be pretty interesting. Okay, maybe just to close the loop on this, to plug in the value of alpha that we actually get when we run our machinery on this collection of events. What is it? Well, the regret bound we get is 2d times what was alpha? Well, alpha was root c times the log of 2 times the number of conditioning events times d plus 1. Okay, so so in the end, for any polynomial collection of subsequences, we get a regret bound scaling with root d, with the dimension, and then with some log terms. Okay. There's about 8 minutes left, so let me not attempt to begin an entirely different application, but let me maybe just say a couple of words about it, because it's sort of a different. On the one hand, it's an application that sounds kind of different, but mathematically is actually very similar to what we just did. Okay, so let me tell you about like an entirely different problem. The problem of making predictions of a categorical label in like a classification problem. Again, so think about one of these ImageNet problems. Every day your self-driving car like transmits to you a bunch of pixels like an image, and your job is to attach one of 1,000 labels to it: stop sign, small child, hot dog, things like that. Okay, and the image might be blurry, like sometimes you're not sure what's in it, and so you want some way of communicating to the user where your uncertainty lies. Okay, and one way to do that is a prediction set. I will, sometimes I'm really certain this is a bicycle. Okay, but sometimes I'm not. And so I don't want to just say this is a bicycle if I only have like 30% confidence this is a bicycle. What I want to do is I want to say this could be one of these four objects. Okay. And the guarantee that I want to have is that, if I'm programmed with some confidence bound, when I say something, I want it to be true 90% of the time, right? When I say, I think the label is an object in this set, say my program confidence bound is 95%. I want that 95% of the time when I say something like that, the label really is in the set. Okay, that's what I want. Say there's k labels. Okay, so first of all, this is another one of these combinatorial problems. There's 2 to the k possible predictions. Now, how would I do that? Well, if you take like a standard, ResNet kind of classifier, something you'd use to solve a vision problem, it'll produce class scores. It'll produce numbers that look like probabilities, right? It'll sort of look like, bicycle will get, 0.82, hot dog will get 0.05, right? They'll be, they'll look like probabilities in that they are non-negative numbers that sum to 1. Okay, and sort of like you sort of treat them as if they're probabilities, like they're supposed to be, your confidence is somehow supposed to be monotone in these things, right? Like the typical thing to do if you need to make a point prediction is to take the label that has highest score. Okay. Now suppose you needed to produce a prediction set. Suppose, and suppose, these really were real probabilities. Of course, they're not. In fact, if you think too hard about what it even means, the probability that it's a bicycle conditional on the pixels, like, you might go crazy. But don't worry about that. Suppose those were like real probabilities. Okay? Then it would be very clear how you would produce the smallest prediction set that covers the label 95% of the time. You would sort the labels in decreasing order by their true probability. Right? Bicycle, 82%, stop sign, 2%, so on and so forth. And you would take the labels starting from the most probable, and you would stuff them in your prediction set one at a time until the cumulative probability mass in your prediction set exceeded 95%, and then you would stop. Okay? Now you could do that with your scores from your ResNet model, but like it wouldn't have any guarantees because they're not probabilities. Okay? Nevertheless, that's one way in which you could map scores to prediction sets. Think about it as a best response function. It says, okay, given a vector of class scores, what I'm going to do is I'm going to sort them. I'm going to stuff them in my prediction set until the cumulative class scores sum up to 95%. That's some mapping from class scores to prediction set. Okay? You could have other mappings, but like this is a reasonable. Now, pick a particular prediction set that has, 3 labels in it. Bicycle, hot dog, child. Okay? What is the probability that the true label is in there? Well, it's the probability that the true label was bicycle plus the probability that the true label was hot dog plus the probability the true label was child. The sum of the probabilities of the things you've included. It's a lot like the structure here in this sort of online combinatorial optimization setting where your gain is the sum of the gains of the atomic actions, right? The labels here, think about them as atomic actions. The prediction sets, think of them as the compound act, okay? The coverage probability of a prediction set is the sum of the coverage probabilities of the base actions of the label scores. Okay, so if I want to do this using the technology we've developed, what am I going to do? If I have 1,000 labels, I'm going to predict class scores for them. I'm going to make predictions that are probabilities, that are, my prediction space is the simplex over the 1,000 labels. Okay? What do I want if I want my prediction set algorithm to have the coverage I think it will? I want that my class scores should be unbiased, not just overall, but conditional on the decision that my prediction set algorithm, given these class scores, includes the label. So I want that my predicted class scores should be unbiased, conditional on my prediction set algorithm, mapping them onto a prediction set that includes a hot dog. I want my class scores to be unbiased, conditional on my prediction set algorithm, mapping them onto a prediction set that includes a small child. Okay. K labels only K conditioning events. And for reasons that are very similar to what we just worked out, using a very similar linear structure here in online combinatorial optimization, if you do this, and you can do this simultaneously, not just for one mapping from prediction, from class scores to prediction sets, but for any polynomial collection of mappings, if you do this, then you can treat the class scores as if they are true probabilities for the purposes of producing prediction sets. And indeed, they will behave as if they are true probabilities. The coverage guarantees of those prediction sets will be exactly what you thought they were because of these bias properties. Okay, and you can do this, without sacrificing the accuracy of your favorite model. If you have, through long effort and blood, sweat, and tears, trained a model that is like really good at distinguishing between small children and hot dogs, then I can use that model and define conditioning events as a function of that model, as a function of the level sets of that model, and get these kinds of prediction set guarantees without, with sort of predictive error, like squared error or cross entropy loss or whatever is your favorite loss function, that is at least as good as the model you started with. So sort of calibrating the class probabilities, not in the sense of full 1,000-dimensional calibration, which is out of reach, but calibrating them specifically to be useful for producing prediction sets gives you an efficient algorithm that gives prediction sets with the guarantees you would have had you been predicting true probabilities without sacrificing accuracy. Okay, and again, the math is basically the same as this because coverage as a function of the class probabilities is linear. The probability your set covers the label is just the sum of the probabilities of the labels within the set. Okay. Thank you, everybody, for attending the class. I hope you learned something. And that's it.